Welcome to Unit 1 for AP Statistics. This first unit is about exploring one variable data and to relate it to the textbook that you've got a copy of. This is pretty much what Chapter 1 is. As we go through all these lectures throughout the course of the year, the course I have refashioned to be more like what the College Board has given me, which is in these units. The units do not correspond to the units or chapters in the book directly. It just so happens that it starts in Chapter 1 of the book as well. You will be given homework in the textbook based on the chapters, and it turns out that hopefully after this video, Chapter 1 will be done, and you'll have your Chapter 1 assignment, and then we'll just keep rolling in future days with future videos. The way these videos will work best is if you've got some paper handy that you can take notes in. If you just watch these videos and not take notes, this might as well be a fun movie that you forget the next day. So if you don't have paper with you, go ahead, pause the video, grab some, resume when you're back with some paper. All right, let's go. So I had a really interesting activity planned for the second day of school. But since we're not at school, we'll still talk about how it would go. But instead of getting the data during class, we'll find another way. But here's the activity. I would like to know whether people can distinguish Coke from Pepsi. Some people will absolutely say, yes, I can tell the difference between those two. Maybe they're telling the truth, maybe not. And other people, honestly, probably couldn't tell the difference anyway. There are similar experiments that have been done comparing tap water to bottled water. You could do the same thing. But the way to test whether people can actually tell the difference is you have each person. So let's say I want to know whether this class, everyone in this class, can distinguish the two. What I would do is I would have each person drink from 3 different cups. 2 of the cups would have one of these drinks. The third cup would have the other. So if you could think of all the possible combinations of the two, so we could have cup A, B, and C. All the possible different combinations could be Coke, Pepsi, Pepsi, Coke, Coke, Pepsi, Coke, Pepsi, Coke, Pepsi, Pepsi, Coke, Pepsi, Coke, Pepsi, and Pepsi, Coke, Coke. I believe those are the 6 different combinations that you can have where you've got 2 of one drink and 1 of the other. So we don't have any Coke, 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 or Pepsi, Pepsi, Pepsi. That would be kind of cruel to suggest that one of those would be different. So these are the 6. And the order matters, right? Coke, Pepsi, Pepsi is different from Pepsi, Coke, Pepsi. Or, the other ones. They're all different because you don't want the first glass necessarily, or the first cup being influential, right? So if the first one tastes different than the other 2, maybe that would tip someone off more than if it was the second one or the third one. Who knows, right? We don't want that to bias the results, which combination we've got here. So what we would do is we would randomly assign one of these combinations to each person. So what we could do is roll a die. So we've got a die roll here. Die roll. And the reason I would choose to roll a die, 1, it's random what you get, and 2, there are 6 possibilities. 6 different numbers you can get on a die. So let's just assign a number to each of those possibilities. We'll roll a die. Say the first time I roll, I get a 4. I would fill the first 2 cups with Pepsi and the third cup with Coke. and the first individual being experimented upon would drink from all three and say which one's different. Okay? Maybe the next time I roll, I give it 2, Coke, Pepsi, give them to a person, see which one they think is different. So on and so forth. We could do that for everyone in the class. Okay? So all these combinations would be equally likely and determined at random. And this is important because if it's not done at random, like we said, there could be bias that, now that I think about it, maybe the different one being the third one would be the most likely to be caught on, right? You take a sip, you take another sip, you think, oh, that's pretty similar. Take the sip of the third one, you're like, that's different. Okay. So, our goal is for an individual person to identify which cup is different from the others. So, once you drink from all 3 cups, and you say which cup you think is different, you're either right or wrong. So let's suppose nobody could tell the difference between Coke and Pepsi. Let's just say everyone goes through this experiment, they drink from the 3 cups, they have no idea, they taste exactly the same, and they just guess at random which one's different. If 15 people do this, so let's say the class that we're trying to figure out who knows the difference has 15 people in it. If 15 people do this and guess at random which cup is different, how many people do you expect to get it right if they're guessing? If they're guessing, if they really don't have any idea. Well, in order to answer this, and you might have an idea, you need to know what the probability of guessing the right cup is. And I say the word probability, I don't want that to scare you at all. A lot of people are really scared about probability in general. There are 3 cups, right? And one of them is always the one that's different. Sometimes it's A, sometimes it's B, sometimes it's C, right? What are the chances of guessing the right cup at random? There's 1 right cup out of 3. So the probability of getting the right cup is 1 in 3. So we would expect 1 out of every 3 people to get it right, right? So if 15 people are doing it, and we expect 1 out of every 3 people to get it right, then we expect five people to get it right, right? So let's say that we do this experiment. And let's say 6 people get it right. That's more than 5. Is that proof that those students know the difference? Or is it possible to get 6 right, 6 people guess the right one, even if they're just guessing? If they're just guessing, could this number be different if we actually do it? Is 6 different enough to convince you that they know the difference? What if 9 people got it right? What if 12 people got it right? How many would have to be correct before you were convinced that they could tell the difference? It's an interesting question. And maybe one that we'll get an answer to by the end of this video. Maybe, just maybe. So, let's say 15 people do this, 12 get the right cup. 12 respond with the right answer. That's a lot more than we would expect if they were just guessing at random. So, if 12 people were right, what could we say about those students? we're pretty sure, since this is so much higher than 5 out of 15, they're not just guessing, right? Someone knows the difference between Coke and Pepsi if 12 out of 15 are right. So this is something we could conclude. If 12 of those 15 students got the right answer, then we can conclude at least some of them can tell the difference, truly, between Coke and Pepsi. Now, we're not saying they all can. It's not like they all got the right answer. Even if they all got the right answer, that wouldn't necessarily mean they all know the difference. Maybe some just took a lucky guess, right? But since this number is so much bigger than what we would expect at random, we can say that at least some of them know the difference. I think that's reasonable. So how many students would have to be correct for you to believe they weren't just guessing? How many would have to be right? If only 5 out of 15 are right, they're probably just guessing. That's what we would expect if they were just guessing. 12 out of 15, we're convinced that at least some of them know. So the number for this, the answer to this question, is probably somewhere in between 5 and 12. But what number is it? How many would have to get it right for you to be convinced? If only there were a way we could figure this out. That would be great. Let's bring in some dice. All right, so let's try and figure out the answer to the question. To do that, I'd like you, if possible, to go to the homepage for the Canvas course. And if you're having trouble doing that while you're watching the video, my apologies. Let's talk about going to Unit 1 and going to the daily lessons here. And here you can see a link to some virtual dice. And this is random.org. So let's go here. And this allows you to roll virtual dice. So the randomness comes from atmospheric noise, blah, 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 blah. We don't know anything about that yet. That's okay. So you can roll any number of virtual dice here. So I can roll 1 die, and I rolled a 1. And I can roll it again, I roll a 3. And does this not look random to you? Check out the FAQ. That's a lot of explanation as to how this is truly random, and we'll talk about that later in the course. But we've established that there is a 1 in 3 chance that a student would guess the right cup at random. So let's see if we can figure out how many times we would expect a student to get it right at random. We already know it's approximately 1/3. We know we would expect 5 out of 15. But what would actually happen? Sometimes we'll get more, sometimes we'll get less. What numbers are reasonable? We can use these virtual dice to answer that question. So let's go ahead and go back. And we said that there were 15 students that were doing this. So let's roll 15 dice. Now, we know the chances of them guessing the right cup correctly are 1 in 3. Each one of these dice has 6 possible results. So how can we simulate someone guessing the right cup if the chances are 1 in 3? Well, we can assign certain numbers of the dice to getting the correct cup. So if there are 6 outcomes for the dice, maybe getting a 1 or a 2 could represent getting the right cup as a guess. So if we roll 15 dice, one represents each student. If any of those dice are ones or twos, we'll say that that means they got the right guess. If it's a 3, a 4, a 5, or a 6, we'll say that that means they got it wrong. Okay? So if we roll 15 dice here, this is what we get. So we're counting the ones and the twos. Those are the people that got it right. So that's a 2, a 1, a 1, a 1, a 2, a 1, a 1, and a 2. Wow, a lot of people guessed right here. That's 1, 2, 3, 4, 5, 6, 7, 8. So that would be 8 out of 15 people getting it right. If we roll the 15 dice again, we get a different outcome. This time we get 1, 2, 3, 4, 5, 6, 7, 8 again. That's weird. Let's do it again. Okay, this time we only got 1, 2 people that got it right. We're counting the ones and twos. So there is variability involved. It's not going to be 5 out of 15 every single time. What I would like you to do is pause the video in a second and roll these 15 dice at least 10 times. You can do it as many times as you want. If you really want to do it all day, you can. But do it at least 10 times and record the number of students that got it right every time. Remember, you're only counting the ones and the twos. So here we have 2 ones and no twos, so 2 out of 15 students got it right. So you would record a 2. The next time you roll the dice, you would record however many out of 15 that time. Do it at least 10 times, and when you're done, unpause the video, and we'll see what happens. All right, so I simulated 15 dice rolls 20 times. I did that 20 times and I recorded the results. So here I've made a table, a frequency table of the results. So on this top row is the number of students with the correct guess. So anything from 0 up to 10. And then I've got how many times that happened out of the 20 times that I did it. So I never got 0. There was always at least 1 or 2 on all the dice. I got 1 or 2, which means 1 student guessed correctly once out of these 20 times. I got 2 of them twice, 3 of them 4 times, 4 correct twice, 5 correct 7 times, 6 correct 3 times, 7 correct once, and I never got anything 8 or higher. Never. Okay? So, from this frequency table, you can start to see the shape of the distribution of numbers of students with the correct guess. The most popular result was that 5 students get it correct. Amazing! That's what we would expect to happen most often. But notice, there is some variability here. Sometimes there were fewer than 5. Sometimes there were more than 5. I did this before I started filming this video. So a few minutes ago when I did it randomly, the first 2 times I simulated 15 dice, I got 8 twice in a row. That didn't happen a single time when I did it 20 times. So who knows why that happened. It's just crazy randomness, right? But we can take the information in this table and make a graph out of it, which should make things even easier to see. So, making a nice little histogram here. 0 happened no times, so there's not going to be anything there. 1 student got a correct guess once, so the number of students that are correct is across my x-axis here, and the frequency is on the y-axis. So with 1 student correct, the frequency was 1. So that gets a nice little bar there. 2 students correct twice. 3 students correct 4 times. Yeah. I don't make the best histograms. Not to scale. 4 happened twice. 5 happened 7 times. That's all the way to the top. 6 happened 3 times. 7 happened once. and anything 8 and above is a 0. So, if you recorded your results, you could summarize those results in a frequency table like this, and from that table you could make a histogram like this. And your shape will probably be different than mine. First of all, you might have only done it 10 times. You might have done it 500 times. Who knows, right? The more times you do this, the more accurate your shape is going to be compared to what we might expect. Okay? The fewer times you do it, that random variation could really show up. But the more times you do it, the more you're going to end up with something you would expect to see. But we're saying we would expect 5 people to get it right. And it turns out, yes. At least in this simulation, that was the most popular number that came up, is that 5 would get it right. But we've seen that there are also times where 4, 3, 2, or even 1 person out of 15 got it right, if they were just guessing, right? This entire simulation was based on the fact that they were purely guessing, that no one knows the difference. So if they're guessing, these are the possible results that we could see. 5, sometimes a little lower, sometimes a little higher. Okay? And your results are going to be different than mine, probably. If you got exactly the same thing, I'd be a little concerned, right? But this gives us an idea of what the likely results are if people were guessing. This is the question we want to answer. How many students would have to be correct for you to believe they weren't just guessing? This is if they're guessing. So what's the number? It's still a little dangerous to answer that question based on this simulation. We only ran it 20 times. You may have run it more, but maybe you ran it less. Can we be confident in saying 8 is that number? That if 8 students out of 15 got it right, then that means they weren't guessing? Maybe. We didn't see it, but in the demo that I showed you, it happened twice in a row. Maybe 9's the number. Maybe 10's the number, right? So we still don't know for sure. And that's one of the great things about statistics, is that while we can say what that number might be, there's no way to know for sure. Is it possible that when you randomize those 15 dice that they're all 1s and 2s? All 15 of them? It could happen, right? It's super unlikely, but it's possible. If we ran that simulation thousands and thousands or millions of times, 15 would come up eventually. You would get a streak of 15 1s and 2s. Does that mean they weren't guessing? No. That just happened by chance. But we're talking about the difference between what is likely and what is unlikely. It is likely to get something in this range. Obviously, the closer you get to 5 in general, the more likely that result is. Things way out on the ends, those are the unlikely ones. What's the tipping point where we would be convinced that they're not guessing? That's a question we're not even really going to try to answer until next semester. We've got to build up to answering that type of question. It's a lot more difficult to come up with than you might think. And even then, we're not certain. There's still some uncertainty involved. But I hope that this example kind of gets your feet wet in terms of the questions that we're going to be asking in this class. And this example might seem a little silly. It's just Coke versus Pepsi. We didn't even do the activity, which kind of cheapens it a little bit. But you can have data that's much more consequential than what we're talking about here and use these same ideas to come up with answers to these questions. What's the likelihood that someone develops serious complications from COVID-19 or dies? You could run simulations, and in fact, that's what people are doing to come up with the projections of how many people are going to pass away, how many people are going to be admitted to the hospital. This is how we knew when it was safe to open up so that the hospitals wouldn't be overwhelmed. they had people running these statistical simulations to try and account for everything and see what could happen. So, I hope this was an interesting first activity for you. I hope you enjoyed rolling the virtual dice. I think we'll get back to using that again later in the class. But we've actually covered everything in Chapter 1. So if you look at Canvas, if you go to that Chapter 1 or Unit 1 homepage, you'll see a link to the Chapter 1 homework assignment. Please look at those problems and complete them by the due date listed on Canvas. It is important for you to do that. I really want to see what you come up with for your work. I will have virtual office hours at some time before that assignment is due. So if you want or need to ask questions live one-on-one with me, you should have an opportunity to do that. If you can't make it or you choose to ask your questions in a different way, you can text me on Remind, you can shoot me an email, and we will figure out a way to make it work. If you have any questions on that assignment, please do not hesitate to contact me. I love helping students out. It's one of the reasons I'm doing this job, right? So, that's it for Chapter 1. Do your assignment, and we will see you in the next video. Have a good day.